Hey everybody! In this video, we'll discuss the notion of projectibility and the so-called new problem of induction, or the Grue paradox. Before we do so though, I just want to recap where we're at in the course. Right? So this is a logic course, and in particular it's a course on inductive logic. Right? We've been viewing logic in this course as a study of proper argumentation, or in particular proper inference. Right? Logic helps us identify good inferences and distinguish them from bad inferences. The difference between deductive logic and inductive logic, where deductive logic is what we study in the LPS 30 and other logic courses, and inductive logic is what we focus on in this course, lies in the different standards that these two branches of logic employ in evaluating the quality of an argument's inference. In the case of deductive logic, the standard was validity, right? A good argument is one whose premises guarantee the truth of its conclusion. In other words, it's impossible for the premises of a valid argument to be true while its conclusion is false. Last week we looked at one formal system for deductive logic, as propositional logic, and we saw that it gave us a rigorous method for assessing the validity of at least some arguments, right? And that was the method of truth tables. If we wanted to look further at deductive logic, we would build up more sophisticated formal logics like predicate logic or modal logics, that would give us further formal tools to help us to assess the validity of an even wider class of arguments. But instead, we're going to look at inductive logic, right? And here the standard of good inference is inductive strength, right? On this standard, a good argument is one whose premises, if true, render its conclusion probable or likely to be true. And we can in general say that one argument's inference is inductively better than another argument's inference, just in case the first argument's conclusion, given the truth of its premises, is more likely than the conclusion of the second argument, given the truth of its premises. So that's the sort of logic that we're looking at, right? And that's all well and good, but as we noted, it's a little bit vague, right? A rigorous system of inductive logic should give us a precise notion of inductive probability, right? What does it mean for a set of premises to render a conclusion probable? Further, once we have a precise understanding of this notion in hand, we want inductive logic to give us a rigorous and methodical way to measure the inductive strength of different arguments, just like truth tables gave us a clear way to assess the validity of at least some arguments, right? Namely, arguments whose validity turned upon their use of the logical connectives and or and not. Furthermore, we want our inductive logic to be scientific in the sense that we want its verdicts about the relative inductive strength of different arguments to accord well with common sense and scientific practice. Right? Coming up with such a system of scientific inductive logic is what we've called the first problem of inductive logic, right? Or the problem of constructing a scientific logic. This week we've been looking at a second problem that confronts inductive logic, namely the problem of rationally justifying scientific inductive logic, right? This is the old philosophical problem that dates back to David Hume, and we've been calling it the traditional problem of induction. Note that we didn't need to handle the first problem of constructing a scientific inductive logic before the second, because Hume's argument was general enough to cause problems regardless of the details of how we construct our scientific inductive logic. All we had to assume was that scientific inductive logic will consist of rules for assigning inductive probabilities to various arguments, and that will assume, at least in a vague sense, that nature is uniform and the future will resemble the past. Hume argued that we could never rationally justify any system of this sort, and we looked at three possible responses to Hume and concluded that regardless of the many merits of these proposals, the problem is a rich and interesting one to think about philosophically. Nonetheless, now we're going to set this deep philosophy aside for the moment, at least. We'll get into some more deep philosophy as we go on. And today we're going to start to think a little more about the first problem of inductive logic. That is the problem of constructing rather than justifying scientific inductive logic. To try to make some headway on this problem, we're going to consider the notion of projection or projectibility. Okay? So that's where we'll start with the new material for today. All right. So scientific inductive logic, we can say, at least at an intuitive level, projects observed regularities, right? Now, what does this mean, right? It's helpful to see this through considering some intuitively strong arguments, right? So consider this argument. all observed emeralds have been green, therefore the next emerald to be observed will be green. Right? This is intuitively and inductively strong argument. And it seems like what it's doing, right, is it's projecting an observed regularity, something that we've seen in the data that we've observed so far, something that's in our stock of knowledge, right? Namely, that all the emeralds we've observed so far have been green. We're projecting that out onto unobserved cases, right? The next emerald, which we haven't observed yet, but which we will observe, we predict will be green, right? So we're projecting from the data that we have to the unobserved cases. Here's an example of weak, inductively weak argument, right? All observed emeralds have been green. The next emerald to be observed will not be green, right? This is intuitively, it's a weak inductive argument, and it does not do this sort of projection, right? We've observed that a bunch of emeralds are green, or all the emeralds we've observed have been green, and we're projecting that the unobserved cases will be different than the observed cases, right? Intuitively, that's not what we want to do in scientific inductive logic, right? So I think that, right, in general, we have this sort of formal argument pattern we're employing, right? We have a premise that states that all observed x's, all observed members of some class, have been y's. They've had some property, right? They've been members of some second class, right? And then we conclude that the next x we observe will also be a y, right? So an example of this sort of argument, right, let's see, would be, right, exactly this argument we had before. All observed emeralds have been green. The next emerald, therefore the next emerald to be observed will be green, right? And this is just the formal argument structure that we have, okay? Now we could tweak this a little bit and consider a slightly weaker argument, but that still seems like it's fairly strong, right? So here we have a premise like 99% of the observed x's have been y's, therefore the next x to be observed will be y, right? And we could imagine further iterations of this, 98%, 97%, and so on, right? Each one getting a little weaker than the next, but still having some force to them, right? So this suggests perhaps the following general rule for assigning inductive probabilities to arguments of this form. We might say that the inductive probability of an argument of the form n% of observed x's have been y's, therefore the next x to be observed will be a y, is just n over 100, right? So in the case where all x's have been y's, or 100% of the x's have been y's, we'd assign the corresponding argument of a maximal inductive probability of 1. In the case where only half, or 50% of the x's have been y's, we'd assign it an inductive probability of just 0.5, right? Okay, so this is at least, perhaps you might think, a start to building a formal inductive logic. So here's an example of an argument where we could apply this, right? We might have a premise that 85% of observed ogres are swamp dwellers. They live in the swamp. Therefore, the next ogre we observe will be a swamp dweller, right? This argument, by rule S, would be assigned inductive probability 0.85, right? So rule S gives us a way of assigning inductive probabilities to arguments that take on this form. Now, the first problem with rule S is that it has very limited applications, right? Obviously, it only applies to arguments that take on a very particular form, and there's lots of arguments that we want to assign inductive probability to via scientific inductive logic that don't take on that form, right? So it has limited application. So, for example, consider even an argument like the ones we have here, right? 10 emeralds have been observed, 90% of observed emeralds are green, thus the next emerald to be observed will be green, right? This doesn't take on exactly the form that we had, or that was referenced in rule S, so rule S is not going to tell us exactly how to assign an inductive probability to it. Or consider the argument, 1 million emeralds have been observed, 90% of observed emeralds have been green, thus the next emerald to be observed will be green, right? Now, intuitively, right, we have two cases here where the argument is claiming that in the premises that 90% of observed emeralds have been green, but in one case, there's a very small data set with a very small sample size, right? Only 10 emeralds. In the other case, it's much larger. We have 1 million emeralds, right? So intuitively, right, the second argument is going to be much stronger than the first argument, and we want that to be recognized in our scientific inductive logic, and rule S doesn't give us any way of recognizing that, right? So that's the first sort of issue that we want to be thinking about. Here's another sort of issue, right? Consider this argument. Every person who has taken drug X has had no side effects. Second premise, drug X has only been administered to healthy people between 20 and 25. Conclusion, thus the next person to take drug X will have no side effects, right? This might give us, right, some reason, it seems like these premises give us some reason to think that the next person to take drug X will have no side effects. But you might worry, I mean, maybe the next person to take drug X is going to be an older person or someone outside the age range of 20-25 or someone who's not super healthy. And then we don't have as much good data here supporting the claim that they won't have some sort of bad side effect. Contrast that with the argument, every person who has taken drug X has had no side effects. Drug X has been administered to people of all ages and health conditions. Therefore, the next person to take drug X will have no side effects. Intuitively, this is a much stronger inductive argument because it's the quality of the data that's referenced in premise 2 is a much better quality than in the first argument. Right? So again, rule S is not going to help us distinguish these arguments. It's not going to tell us how to assign inductive probabilities to these arguments. So rule S has very limited application. Okay. There's a deeper worry regarding rule S, though, namely that it gives wrong verdicts and perhaps even inconsistent verdicts, right? So to bring out this, we're going to talk about the notion of projectibility. So the problem for rule S is that certain predicates, or what we called in the video lecture we did on statements, characterizing expressions, seem to be projectable, while others do not, right? Now, a predicate we'll say is projectable just in case it can reasonably be employed in an argument form to which rule S applies, right? So an argument form like n% of x's have been y's, therefore the next x will be y. Right? Okay. Now we cannot treat every predicate as projectable on pain of rendering rule S inconsistent, right? Or so we're going to claim, right? Because you might think, well, why not just have every predicate qualify as projectable, and we could apply rule S to all of them and everything would be fine. The worry is that that's going to really lead us to inconsistency. And the argument for why this leads us to inconsistency is what's known as the new problem of induction, or sometimes called the new riddle of induction, right? Contrasting it with Hume's traditional problem of induction or old problem of induction that we've been discussing during this week. This is also known as the group paradox. And it was originally developed by Nelson Goodman, who was a 20th century philosopher in a famous book he wrote on this and other topics. All right, so how are we going to make this case that not every predicate, not every characterizing expression can be projectable, can reasonably be employed in an argument of the form that rule S applies to? Well, our counterexample to considering every predicate as projectable is going to be what's known as GRU, right? Define an object to be GRU at a time t, just in case, 1, the object is green and it's before 2100 AD, or the object is blue and t is after 2100 AD, right? So GRU here is a color predicate, right? Once we know the color of an object at a particular time, and we know the time, we know whether the object is GRU at that time or not, right? All right, so suppose that we make the following inference prior to the first observation of an emerald in 2100 AD, right? So maybe it's 2099 AD, December 31st, we're anticipating making another observation of emerald in the new year, right, after 2100. So our first premise is that all observed emeralds have been GRU. Now that's a true premise, right? Because prior to 2100 AD, what it is for an emerald to be GRU is to be green, right? Because an emerald is GRU, just in case it's green prior to 2100 AD, right? So we have a true premise, a premise that amounts to basically saying that all emeralds have been green, right? All observed emeralds have been green, all observed emeralds have been GRU. Right? The conclusion then is that the next emerald to be observed will be GRU, right? That we're projecting the GRU predicate from the observed cases onto the unobserved cases, right? But the next emerald to be observed will be observed after 2100 AD, right? So for it to be GRU at that time is going to be for it to be blue. So we're effectively concluding that the emerald to be observed will be blue. The next emerald to be observed will be blue, right? So rule S is going to render this an inductively strong argument because the premise is true, right? And we're just projecting the GRU predicate in an argument of the form to which rule S applies. So rule S is going to render this an inductively strong argument, even though we end up concluding that the next emerald will be blue, right? Which is intuitively a crazy inference to make, right? We've seen that all the emeralds are green, we shouldn't be concluding it's going to be blue next time. Right? Now, rule S would also render the following intuitively correctly inductively strong argument inductively strong, right? This is an argument where we end up concluding the next emerald will be green, right? It takes the natural form. All observed emeralds have been green so far. Therefore, the next emerald to be observed will be green. So now we have rule S telling us that we have two inductively strong arguments, right? That have effectively equivalent premises, right? Premises claiming prior to 2100 AD that all of the emeralds we've observed have been either green or grew, right? Depending on the argument we're looking at. But the arguments have conflicting conclusions, right? Inconsistent conclusions, right? One claiming that the next emerald to be observed will be green, the other claiming that the next emerald to be observed will be blue, right? So rule S has caused us to see arguments with equivalent premises and conflicting conclusions as both being of high inductive probability. And that's a major problem, right? We don't want our scientific inductive logic to do that. The problem here, right, is that GRU is really an unprojectable predicate, right? We shouldn't be projecting from the fact that all observed emeralds so far have been GRU to the claim that the next emerald to be observed will be GRU, right? But now this gives us a problem, right? We have to figure out exactly why GRU is pathological and figure out which predicates are projectable and which are unprojectable, like GRU, right? So which ones are projectable, like green, we said was a good projectable predicate, and which ones are unprojectable, like GRU, right? So this then gives us a big task for scientific inductive logic, right? And we can compare this actually to some of our discussion of the uniformity of nature in the case of the old problem of induction, right? Recall that we said that scientific inductive logic assumes in some sense that nature is uniform, right? All observed emeralds are green, therefore the next emerald to be observed will be green, right? We're assuming that there's a certain uniformity there to nature, right? We can project, that's almost right, the same as saying that that green predicate is projectable, right? But nature can't be uniform in every respect, as unprojectable predicates demonstrate, right? So we can't move from the fact that all the emeralds have been GRU so far to the claim that the next emerald to be observed will be GRU, right? That's not the sort of thing, the sort of uniformity that's going to obtain in nature. So figuring out which predicates are projectable is in some ways analogous to figuring out in which respects nature is going to be uniform, right? It's going to be uniform in that emeralds will continue to be green, but it's not going to be uniform in the sense that emeralds are not going to continue to be GRU. Right? So what scientific inductive logic then has to do is not merely justify the claim that nature is uniform, which is what we were trying to do to answer to the traditional problem of induction, but we also have to specify the respects in which nature is uniform, right? Specify which predicates are projectable. And that's the new problem of induction, okay? All right, so this gives you at least some taste for this new problem of induction, which is like the old problem, I think a really rich and interesting philosophical problem. It raises a lot of fascinating questions. A lot of ink has been spilt on this. It's something that, again, I encourage you, if you're interested in it, you can read more about it, look at some more proposed solutions that people have. But we'll end our course's discussion of this problem here. And next week, we'll move on to looking at some new topics as we try to advance towards building up to an actual scientific inductive logic. And thanks for watching. Please complete the participation poll for this video. And that will be due, remember, not until Monday at midnight. So you'll have all the way until then to do that. And it should be a pretty easy participation poll for this video. All right. Thanks, guys.